How's everyone doing today? All right. Glad everyone could make it this morning on time. I think we'll go ahead and get started. First of all, were there any questions over what we covered last time? All right. Well, let me know if we do have questions, and we'll just jump right back into this thing. Um, so last time we started talking about factoring, and that was the first of a few different methods that we would use to solve quadratic equations. We had one more thing I wanted to do with that, and then we'll move on to the other topics. The goal today is to complete 1.2 and also 1.3, which I believe we can do easily. But let me get my book out real quick. Yeah, definitely we'll be able to get through all of that today. Perhaps even a little bit more, but we may just stop after we finish that. Yeah, that's probably good. All right. Make sure my book was open behind me so I can get it if I need it. All right. That's good. We're starting, and looks like there's 28 people here, and that's great. Yeah. Hope you all are having a good morning too. I'm still adjusting to this morning schedule since I was off all summer, and basically I get up every day around 11 a.m. So it's been a transition going back to last week, but maybe in another couple of weeks I'll feel a little bit better about getting up for an 8 o'clock class. I don't mind teaching the class at all. I just have to adjust my schedule, and that's usually how it is. If I have too much time off, things just go crazy. So, especially the way things are now, it's just I feel like I've been sleeping a lot more. So, anyway, I meant to get a problem out of the book. Sorry. All right. This is a continuation of section 1.2. And we hadn't looked at any problems like this, but there's one or two definitely there in the book that I feel like we need to discuss. And this is the only other type of example that we needed to look at for factoring itself. And that is the case where we start off with what's called a rational equation. Rational means that we have a fraction that's present in the equation. Probably not our favorite thing to have to deal with, but it turns out it's actually not that difficult to deal with in a lot of cases. Sometimes it can be a little more involved, but as long as we understand the steps that we need to take and we can carry them out effectively, then we'll be able to move past that. So whenever we have a problem and there's a denominator here, remember first of all that the other terms in the problem also have denominators to begin with. But we really just want to find a common denominator for all three terms. And usually the easiest way to do that is just to multiply them together. Now, really, because x is our only denominator other than 1, we can just use x as our common denominator in this case. But if we had two terms that had different denominators, for instance, then their product would be the common denominator. So our lowest common denominator in this case is x. So we would take this entire expression and multiply each term by x. So x times x gives us x squared. X times 12 over x. That one's a little bit tricky because it involves knowledge of working with fractions. When we multiply by x, we're actually only multiplying the numerator by x. So there's 12x on top, and then the x on the bottom stays the same. So we can cancel those out. And then we still have 7 times x on the right hand side. Now, effectively what happens is we've gotten rid of the fraction there, and that's actually the goal. Anytime we have a problem where it's an equation and we start off with a fraction of some kind, we can get rid of that fraction by multiplying by the common denominator like we just did here. Preferably we would multiply by the lowest common denominator, but as long as it's any common denominator it would work. So once we get to this point and we need to be able to solve for x, we need to be able to factor. Again, the other thing that we need to remember is that in order to factor this, it has to be equal to 0. So we'll want to subtract this 7x from both sides. And so that'll give us x squared minus 7x plus 12 is equal to 0. And so now it's to a point where we can go ahead and factor this. And so we need two numbers that multiply to 12 and add to negative 7. And what would those two numbers be? Three and 4, good. There's something else specific that we want to make sure we include, though. It's not just 3 and 4, but negative 3 and negative 4. Right, exactly. So negative 3 and negative 4. Again, we're paying attention to the signs. We want to make sure that to get a positive product and a negative sum, it has to be a pair of negative numbers for that to happen. Negative times negative is positive, but adding two negatives together results in a negative. So that leads to our factorization. X minus 3 times x minus 4 is equal to 0. And so we end up with 3 and 4 as the solutions to this. Now, with rational equations specifically, there is a remote possibility that one of our answers is actually invalid. But the way that we can confirm whether or not they're valid answers is by plugging them back into the original equation. So if we plug in 3, we get 3 plus 12 divided by 3, which is 4. 3 plus 4 equals 7. So that checks out. I mean, that's a true statement. And that's really all we're looking for. And x equals 4. 4 plus 12 divided by 4, which is 4 plus 3. And that's equals 7 also. So both of these check out in this case. Normally we don't have to check our answers, but since we started with the fraction in the original equation, that is one reason we do have to check answers. There's other reasons that we'll discuss next week, but for now that's all we've looked at so far that requires that. Okay, now if we look at this problem, is there any value of x where it would be technically impossible to take 12 and divide by x? Is there any answer that we would potentially consider invalid here? Does anyone know what that is? Anything that we cannot take 12 and divide by the number. 0, yes. Technically, we could divide 12 by anything, but 12 divided by 0 does not really exist. It's basically an impossibility. When we think about the idea of division, when we say 12 divided by 6, we're saying, how many 6's do we need to make 12? Well, we need 2 6's. So 12 divided by 6 is 2. If we want to do 12 divided by 3, how many 3's do we need to equal 12? Well, there's 4 3's in 12. So 12 divided by 3 is 4. Okay? And if we continue down that line, how many zeros do we need to equal 12? Well, we can keep adding zeros together forever, and the answer will still be 0. It will never equal 12. So 12 divided by 0 is an impossibility in that sense. So if we happen to end up with an x equals 0 for this particular problem, then it would have been an invalid solution because we just can't divide by 0. Okay? So division by 0 is undefined. So anytime we run into that, we have to make sure we're checking if that doesn't occur. And that's really the point of checking our answers here, is to make sure we aren't dividing by 0 when we substitute these back into the original question. Okay. So that wraps up our section on factoring. Now, we didn't look at the factoring case where we have a number in front of x squared, but really what I've found is a lot of students prefer to use the quadratic formula in that instance anyway. So I'm going to basically show y'all those types of problems using the quadratic formula instead of worrying about going through the factoring process on those, because it can be somewhat difficult when we have that number in front of x squared. Before we get to that, though, we're going to look at the square root method as our second type of problem that we want to work on. Okay. So our square root method says that if x squared is equal to some number a, and we'll just call it a, then x is equal to plus or minus the square root of a. And the idea is that if we have x squared here equal to a constant, just a number, then we can just take the square root of both sides and say, okay, square root of x squared which is x, and then the square root of a, which is square root of a. Now, whenever we ourselves, as people working the problem, introduce a square root into the problem by taking the square root on both sides, we have to include plus or minus as part of that, because really there's two solutions there. And let's look at why that's true. For example, if we have x squared equals 9, we know we can take the square root of both sides of that equation. So square root of x squared equals plus or minus the square root of 9, which is just 3. So we get x on the left and 3 on the right, but it could be a positive or a negative 3. And that's because if we take a positive 3 and square it, we get 9, of course. But if we take a negative 3 and square that number, when we square a number, that means we're multiplying it by itself. So positive 3 times positive 3 is 9, and negative 3 times negative 3 is also 9. So really, we need both of these answers because both of those are valid right here. So anytime we take the square root, or we introduce the square root into the equation, we always have to include plus or minus on either one side or the other. And usually we, almost always, if not always, we want it on the side there is just a constant. Okay. Now, that's really the fundamentals of the square root method right there. It can be a little bit more challenging in some sense. It just depends on how the problem is presented. Now, we can make it a little bit more complicated problem. Let's say, for example, that's not great. Hang on. Sorry. I'm going to call it 20. Yeah, there we go. So we'll say x plus 3 in parentheses squared minus 5 is equal to 20. Now, initially we may look at that and say, well, what does that have to do with this problem? This is really a problem that we can work in the same way that we approach this problem. It just doesn't necessarily look like it to begin with. And that's a lot of what being comfortable with these different mathematics approaches is about, is knowing that even though there are initially some differences in how problems appear, the approach that we need is still the same at the fundamental level. We can add the 5 over to the right, which maybe seems counterintuitive. I don't know why I drew a line there. I'm sorry. I guess because I was completing the operation. But the idea is that it's still the same as what is presented in the square root method. If we can get an expression that is squared equal to a constant, then we can apply the square root method. Even if we have a more complicated expression like a binomial instead of just a single x, the principle still applies. Now, you bring up a good point. I think it's Brock. The other approach that we could use here is we look at x plus 3 squared, and we might want to go ahead and square that binomial, which would be x squared plus 6x plus 9. And that is absolutely a valid approach. But let me show you how much easier this approach with the square root method is. Yeah, we can take the square root on both sides. And that actually gets rid of the square on the x plus 3, and we just have plus or minus 5 on the right hand side. Okay? So when we have x plus 3 equals plus or minus 5, that means we could have x plus 3 equals positive 5, or x plus 3 is negative 5. And from here we just have to subtract the 3 over. So x is equal to 2, or x is equal to, this would be negative 8. Now, the good news here is that absolutely we could work this problem by squaring the x plus 3 and foiling those and working out what the product is, and then subtracting the 5, and then pulling the 20 back over to the left so it's equal to 0, and we can turn it into a factoring problem, which at this level a factoring problem wouldn't be that difficult. But I think it's so much easier in this case if we can recognize that if we just move the 5 over, we have a situation where we can just take the square root on both sides and get a much simpler approach to solving this problem. But that's what a lot of math is. There are going to be cases where there's multiple ways to work something. Can we recognize the easiest way to do it? Sometimes. Is it absolutely necessary to work it the easiest way possible? No. We know there's multiple ways to work everything in a lot of cases. Especially when we're working with solving quadratic equations, because we always keep in mind the quadratic formula is always a possibility. We haven't looked at it yet, but probably you already know that from previous classes. The quadratic formula literally solves any quadratic equation, which is amazing. We don't technically we have that for cubic equations, but it's nothing that we can really do like on a casual basis. It's really an undertaking to solve a cubic equation using a similar approach. One that requires much more understanding beyond college algebra in a lot of cases. But for square equations, absolutely we can do this, and we can solve it with factoring. We could solve it with the square root method, and we could solve it with the quadratic formula. It's really just a matter of which one we choose to do. Whenever it comes time to take a test, again, I don't have a calendar laid out yet, but I'll make sure I get that up by the end of the week. Whenever we do these problems on the test, you'll be welcome to use whichever method you feel most comfortable with. And it may not be the most efficient method of solving the problem, but it is a method that solves the problem. That's the important thing. Our concern is, can we arrive at the solution successfully? Once we get that down, then we can maybe work on finding the most efficient path to a solution. And even then, it's not of the utmost importance even at this level. I can't really enforce you not using notes, so the answer is I hope you don't, but I also cannot enforce it since it's just a Canvas test, I think, or my hope is that we'll be prepared enough going into the exam that we won't feel the need to use notes, that we'll be comfortable enough answering these questions that we'll be just fine. Okay. Technically the test will be timed, but usually I'll give you like a 2-hour window to complete it. Well, once you start the test, you'll have 2 hours to complete it, but I'll give you a period of over like 5 days during which it must be completed. So you'll have a, you'll be able to pick which time works best for you. So maybe if you're not really a morning person, then you're certainly welcome to take it later in the day if you feel more comfortable doing that. So, yeah. I have, not necessarily in this class, but I have students in other classes that are currently not in this country, even though they're Midland College students, or they're out of state or something like that, because it's easy, since all the classes are online. It's easier just to stay where they normally live than try to come back here and live in Midland when the I'm not sure that I guess the dorms are open, but I don't know how many people are living in there. But anyway, so I always like to be considerate of that, um, just to give everyone a window, like when it's most convenient for them to take, whenever you feel like you're ready. That way, you have a little bit of leeway as far as preparing for the test, also, because I know people are still trying to work also, and you have other classes that you're taking, and one day may not be as good as another. So, absolutely. All right. We're up to 30 viewers, but I only have 25 people in class last I checked. Anyway, it's fine. It's whatever. I just find it odd. I may be incorrect about the number of people in the class. Alright, so the third approach that we look at is the quadratic formula, and probably by the time that we end up taking this exam, you'll have it memorized, but even if you don't have it quite memorized, or you're a little bit fuzzy on where some of the letters go, I will actually provide this formula for you on the test, so it's not strictly necessary to memorize it, although you probably will have it memorized by then. So, quadratic formula says if ax squared plus bx plus c is equal to 0, then x is equal to negative b plus or minus square root of b squared minus 4ac, and then divided by 2a. And probably a lot of you remember that already. Maybe there's one or two details you might be fuzzy on, but yeah, that's our quadratic formula. Notice that we do not take our x's from the formula and plug them in here, or from the original equation and plug them in. The only numbers we're plugging in are the a, the b, and the c, which are the coefficients. So, moving that up a bit. Let's start with this example. 3x squared minus 5x plus 2 is equal to 0. I believe this one is actually factorable, but a lot of the times we may find it easy for these problems where it's factorable, but it has a number besides 1 in front of the x squared, like we have here. It may actually be a lot easier for a lot of students to just go ahead and use the quadratic formula instead. So that's what I really recommend in these instances. And sometimes, if it is factorable, It might take a little more work to do the quadratic formula, but if we're just not sure how to factor something in the first place, then the quadratic formula is an excellent approach to actually solving that problem. So here we have a value of a equals 3, b equals negative 5, c equals 2. And so when we plug those into the quadratic formula, we start with negative b. Now this means the opposite of b. Negative always means opposite. So if b itself is a negative 5 to begin with, then the opposite of b will end up being a positive 5. So we want to make sure we get that straight. And then plus or minus. Now b squared, we're going to have negative 5 squared. And we can go ahead and write that down like so. Negative 5 in parentheses squared. Or if we prefer, we can just write down 25 there if we want. We don't have to do extra steps here if we're comfortable with the calculations that are occurring. So in this first problem, I'm going to go ahead and go through every single step, but in general, it won't be necessary to just write down negative 5 squared if you're comfortable writing 25 down, for instance. So a is 3, so we'll plug that in. Negative 4 times 3 times c, which is 2. And then 2 times a on the bottom, 2 times 3. And again, on the denominator, 2 times 3, we could just write down 6 rather than leaving it as a incomplete multiplication. So even if we take an extra step, it's not a big deal. It's, again, a matter of what level of comfort we have with the material and with what we're doing. So from here, I'm just going through and doing a bit of simplifying. Negative 5 squared we know is 25, minus 4, and then 3 times 2 is 6. And on the bottom, 2 times 3 is 6. Now, this term that's underneath the square root, 25 minus 4 times 6, now we could actually multiply all three of these together, 4 times 3 times 2 in the same step. I split it up for some reason. But we end up with 25 minus 24. So we know that we'll end up with just a 1 under the square root. Now, square root of 1 is just 1. So we can get rid of the radical. Square root of 1 is 1. We write that down. And once we get to this point, 5 plus or minus 1 divided by 6, we can from there go ahead and just split that up into two answers. So we can say 5 plus 1 over 6 and 5 minus 1 over 6. Remember, when we have this plus minus symbol, it technically counts as two different solutions, and so that's why we split it up at this point in the question. 5 plus 1 is 6, and then 6 divided by 6 is 1, and then 5 minus 1 is 4 over 6. Yeah, so 1 and 4 is 6. So I got two answers, although 4 is 6, we could take that a little bit further. And what would that become? 2/3, yeah. So whenever we encounter a fractional answer like that, which we'll now have with these quadratic formula problems, we definitely want to make sure we reduce in the lowest terms. 4/6 is correct. I just want to make sure we take that extra step. Gabriel. Okay. If we did this on the test where you got all the way to this point in the problem, and you wrote it down as 1, and then a 4/6 is the other answer, it's not the end of the world. And like in a 10-point problem, I might take off 1 point. I might take off half a point, to be honest, but I don't know. I could probably do that in the quiz tool if I wanted to take off half a point. It's a minor detail, but still something that we might want to make sure that we do is anytime we have a fraction is reduce it. Okay. So this one was actually factorable, but we're able to still solve the problem by using the quadratic formula. And for a lot of people, I think a lot of students find this method a little bit more palatable anyway as far as working with these terms, because we do in fact get a fractional answer. Okay. So let's do 2x squared minus 5x minus 6 equals 0 as our next example. So we have our A is 2, B is -5, and C is -6. That should be a good problem. Yeah. Anyway, we'll go ahead and plug that into the quadratic formula. So opposite of b, opposite of -5 is +5. B squared, if we square the -5, we get 25 minus 4ac. And on the bottom, 2 times a, which is 2 times 2. We can go ahead and write down a 4 there. So again, these two operations at the very least, the b squared and the 2a, we can go ahead and work out what those are as we write down the number when we plug them into the formula. So I definitely recommend that just as a way of saving ourselves a little bit of time. Where we want to be careful though is the second part of this expression under the square root. So we have 25, but then after that we have minus 4 times 2 times minus 6. So we think about it like this: minus 4 times 2 times -6. Is that result going to be positive or negative? Positive, yeah. Because we know that there's 2 negative signs here, so those are going to cancel out to a positive times the other 2 there, which will still leave it positive. So we go through and multiply that, and it is -4 times 2, which is -8, times -6, which makes it 48. Okay. A little off the page, that's alright. So we get 5 plus or minus the square root of 25 plus 48 under the square root over 4. So this is a spot where we have like these multiple minus signs. We have to be careful that we get that correct, otherwise it basically throws off the rest of the problem from there. Okay. So then we just add together 25 and 48, which is 73. So we get 5 plus or minus the square root of 73 over 4. Now at this point, (73), can we take that square root? Well, 73 is not a perfect square. But beyond perfect squares, if it's something that we can simplify, we want to be able to simplify it. Now 73 in this case is actually what we call a prime number, in that it doesn't have any factors besides 1 in itself. So the reality is here, we cannot simplify this any further. Yeah, and we can check on our calculators, 8.54. It's definitely not a whole number answer, so we don't really want to worry about taking that square root. Yeah. But let me show you what I'm talking about. So that'll just be our answer here. We can't simplify it any further. If we can't do anything with this, we don't worry about doing anything with the rest of it, basically. So if we had ended up with the square root of 40, for instance, we know 40 is also not a perfect square. If we take that square root, it's 6.3 or something like that. But the difference between 73 and 40 is that even though 40 is not a perfect square, it still contains a perfect square as a factor. So we can think of 40 as 4 times 10. Now, the rule is when we have a square root of two numbers that are multiplied together, we can take the square root of the first one times the square root of the second one. So basically the square root, I guess we could say it distributes over multiplication. So basically the square root of a product is equivalent to the product of the square roots. It's not always true about all operations, but we know this one in particular does work. Yeah, and so that'll end up giving us a 2, and then we'll still have a square root of 10. Right. Okay. Now, this one's a little bit more difficult, but the square root of 48. When we split that up into a product, what's the largest perfect square we can take out of 48? So we know that from 40, 4 is a perfect square because the square root of 4 is 2. And that left us with a 10 after that. So we could do 4 times 12. That is one possibility. But it does turn out that 16, that is the better number, right? Yeah, so if we do 16 times 3, and it's okay if you didn't recognize that right off, because I know we don't teach multiples of 16 when we're learning like multiplication tables and things like that. But yeah, 16 times 3 is 48, and that gives us 4 times the square root of 3, right? Because we can go ahead and take the square root of 16 and make that a 4, and then the 3 is still under the square root. We haven't been able to move it out of the square root. So the point of all this is anytime we are working our quadratic formula problem and we get to the point where we simplify the square root portion, we want to make sure that square root, if it's not a perfect square, we break it up in as small of pieces as we can possible. So we want the smallest number left inside that we can get. So 2 square root 10 in the case of root 40, and 4 square root 3 in the case of root 48. But yeah, there are always going to be cases like 73 where we just can't break the number up any further, and that's just our answer right there. Any questions on that? So let's look at another problem where we can utilize that. Three x squared plus 4x minus 4 is equal to 0. Well, that's a good question, Brock. And it's not one that we can easily answer right now, unfortunately. At where we are right now, mathematically, we're still getting the kind of the basics down as far as how we work with polynomial functions, how we work with functions in general. Now, at the end of this section, we are going to introduce a few application problems, but they probably won't give you a great idea of how we might use quadratic formulas. But the truth is that they're part of a larger branch of just being able to solve all equations, and it just depends on what kind of equation the a problem presents us further down the road. So it's like for my Calculus 2 class right now, they're at a point where they've studied all of this material, and they're finally getting to a point where they can really solve real-world problems. Once you get to around trigonometry and Calculus 2, that's where we really start to look at some actual applications of mathematics, whether it's quadratics or other types of formulas. The easiest example we have for quadratic equations, I think, is the falling object problem, as far as when an object is either falling, or if we throw something up in the air vertically, if we know how fast we've thrown it upwards, and we know, well, that's basically it. If we know how quickly we've thrown it upwards, then we can create a formula that is actually a quadratic formula that tells us the height of the object as at whatever time we're interested in. Yeah, and there'll be different opportunities this semester for us to look at some different examples where these are applicable, but a lot of the time the stuff that we do in college algebra is kind of the simplified version of the actual equation. That's just the reality of it. Even when we look at this, like this problem of throwing an object up into the air and seeing, okay, what is its location at time t? After 2 seconds, it's this high. After 4 seconds, the object is this far off the ground, and so on. Even that is somewhat simplified because we're assuming that the object has no drag or air resistance. Is basically able to move through the air freely, which is not common. So it'd be like a perfectly round ball where it has a smooth surface, so the air is not going to catch on it and cause any resistance. So. And that kind of goes back to the old joke, like which falls faster, or which weighs more, a pound of meat or a pound of feathers, and we know that they both weigh a pound. But if we were to drop them, the meat would certainly hit the ground first before the feathers do, because of the way the feathers are structured and the resistance they have against the air. So they gently float to the ground, while a more solid object will fall in a traditional manner. And that's a lot of this. What we end up looking at are physics and chemistry and engineering type applications. And so we'll see a few of these as we go through the textbook, and we'll end up solving them with quadratic equations in some cases, or other equations, as we'll learn later on. But yeah, until you get to some of these later classes, there's only so much insight we can get from looking at the application, unfortunately. Alright. I see one of us is eager to jump ahead. That's fine. I don't think these have... I don't think these have whole or a real answer. Well, they're real answers. I don't think they're rational necessarily, but we'll see how it goes. That's good. Then you'll certainly run into a lot of this stuff, Brock. All right. So let's get this substituted into the quadratic formula. So b in this case is a positive 4, so we'll have negative b is negative 4 plus or minus b squared. 4 squared is 16 minus 4. A is 3 and c is negative 4. And 2 times a, 2 times 3 is 6 on the bottom. Oh, you know what? This does come out. Yeah. I'm sorry, this does come out to be an exact number. That's my bad. So 16, and then we're okay there, but we want to focus on the rest of these numbers. Negative 4 times 3 times negative 4. Now we know that we have two negatives here, so it's going to work out to be a positive. And then 4 times 3 is 12, times 4 is 48. So we end up with a positive 48. (16 plus 48) is what we now have under the square root. And so that's going to give us negative 4 plus or minus the square root of 64 over 6. Yeah, so 64 does turn out to be a perfect square. For some reason I was thinking I was going to get a 48 here, but I forgot about the 16 that was added to it when I was trying to think of a problem. So I got to work harder to get that, I guess. Anyway, we can take the square root of 64, that's 8. So negative 4 plus or minus 8 over 6. Again, plus or minus, we split that up into two different statements. There you go. Yeah, and if you do know a different method and you're comfortable using that, then that's perfectly fine. Like this one turned out to be factorable, so if you wanted to factor this and you're comfortable doing that, absolutely, it's good. So here, let's see, negative 4 plus 8 is 4 over 6, which we know is 2/3. And then 4 minus 8, negative 4 minus 8 is negative 12 over 6, which is negative 2. Okay. Yeah, so 2/3 and negative 2. Yeah. let's try this instead. Three x squared minus 2x plus 3 is equal to 0. So we have A, we have B, and we have C. Now, negative B, or the opposite of B in this case, turns out to be a positive 2. B squared, negative 2 times itself, is positive 4. Let me go ahead and make this a minus 3. Sorry about that. Minus 4 times, or sorry, 4 minus 4 AC. Yeah, it's not factorable, even after I changed the number to a negative. And then 2 times A on the bottom, 2 times 3 is 6. So looking at what we have under the radical here, we have minus 4 times 3 times minus 3. So minus 4 times 3 is minus 12 times minus 3 plus 36. So this time, under the square root, I got a number I wanted us to get, which is positive 40. So x is 2 plus or minus the square root of 40 over 6. Now, I have to turn over to the next page. 246. Okay. Now, we talked about square root of 40 already. We know that the square root of 40 is square root of 4 times 10, which is 2 square root of 10. So what we'll do is we'll go ahead and plug that in for where the square root of 40 is. Sorry about that. And that's over 6. Now, we can reduce this, but we have to be careful about how we reduce this. And this is where it's sometimes a little bit confusing as far as reducing these quadratic formula problems. Now, because we didn't get a whole number square root for square root of 40, we won't have to worry about splitting this up. But we do want to simplify it. We know that we have these 2's on top, and we have a 6 on the bottom. Excuse me. So what I would recommend in this case is we find a common factor to these numbers. So if both of the numbers are 2, then we can factor a 2 out of both places. Okay, so these 2's will factor out. So taking out a 2 leaves 1, so 2 times 1, 2 times 1, those are both 2. And so now we can reduce these two numbers. The key to reducing expressions is that we can only reduce when we have a product in either the numerator or the denominator. For instance, at this stage, we could do 2 over 6 and reduce that, but it wouldn't be correct because we would be ignoring this other half of the numerator. We can't, if these are added and subtracted, we can't reduce one part without changing the other part. And this is where it's a little bit confusing for some students, I know. The reason we factored out the 2 is that now we have this multiplication 2 times this other expression. Once it's down to multiplication, then we can simplify the 2 and the 6 without worrying about how that affects the other part of the numerator because of the multiplication. We'll do that in section 3, Gabriel, which we may not get to today. We may just finish section 2 today. But yeah, we're about there, honestly. And so 2 over 6, we know that's going to be a 1 and a 3. So we can write our solution as x equals, now I'm going to leave it unnecessarily complicated at this point, but we'll be able to fix this. But yeah, we reduce this to 1 over 3. Now, multiplying by 1, we know that really doesn't achieve anything. And so if we don't have to put this top one there if we don't want to. And we don't have to put this 1 right here if we don't want to. In fact, the way that we most usually would see this solution is 1 plus or minus the square root of 10 over 3. Okay, when we multiply 1 times the square root of 10, we can just write square root of 10, and the 1 is implied in front of that. And multiplying this extra 1 on the outside of everything doesn't really affect the values at all, so we can just get rid of that one. Yeah, so we can, or leave our answer in that form, basically. Okay. So that's probably the type of problem that ends up being most involved or potentially confusing, I guess, in the quadratic formula questions, is the instance where the square root, it can be simplified, but it's not a perfect square, so we end up having to simplify the numbers outside of that further, like we see here. Now, beyond solving quadratic equations, there's another aspect of this that we would like to look at, and this is what we call the discriminant. Which is b squared minus 4ac. So you probably recognize this expression because it's the part of the quadratic formula that's actually under the square root. Now b squared minus 4ac, depending on the value here, it tells us what kind of solutions that we can expect from a quadratic equation. For instance, 1, if b squared minus 4ac is greater than 0, then we expect the quadratic equation to have 2 distinct real solutions. And in this case, distinct means that we expect 2 different real number solutions. Second, if b squared minus 4ac happens to equal 0, then we have 1 repeated real solution. And the third outcome, or the third possibility, is that we calculate the value of b squared minus 4ac, and we find that it's less than 0. So it could either be positive, it could be 0, or it could be negative. In the case where we get a negative value under the square root, a negative value for the discriminant, that is where one way that you'll see the book write this is that we have 0 real solutions, but the other way that we can express that is that there's 2 complex or imaginary solutions. Depending on the value. Actually, it doesn't depend on the value. It's almost guaranteed to be complex. Sorry. And so we haven't talked about complex or imaginary numbers just yet. We'll bring that up in section 3. So in this section, you may notice that it writes down in the back of the book 0 real solutions. But in reality, what's happening is that rather than having real solutions, we actually have what we call complex solutions. And we'll talk about that more in section 3. Okay. The other thing that the discriminant is good for is if it's greater than 0, if it happens to equal a perfect square, then that tells us that the polynomial is actually factorable. And that's where, me personally, I find the discriminant more useful, is that by seeing if that's a perfect square, then we can actually factor it or not. Okay. That's not anything that we mentioned in the textbook, though, so you don't have to worry about that particular aspect of the discriminant, but it's just where I find it the most helpful. Okay. So example. Let's use the discriminant I left out an n, sorry. Use the discriminant to find the number of real solutions for, let's say we have 5x squared minus 3x minus 2 is equal to 0. Now, we want to make sure that we don't actually solve this equation. All we're being asked is to figure out how many real solutions does this equation have. And we know based on the discriminant, it's either 2 or 1 or 0. So we look at the value of b squared minus 4ac. b is negative 3 in this case, so we'll square that, it'll be a 9. Minus 4, a is 5, we'll plug that in, and then we'll get a c value of negative 2. So what does that work out to be? Negative 31. Positive. We have some conflicting answers. Very conflicting answers, which is okay. We're still learning. Some of you have part of the answer. I mean, when we combine everything here together. 49, yes. Yeah. This ends up being 9 plus 40, which gives us a value of 49. Yeah, we get two negatives here, which results in a positive. Negative and negative, positive. 4 times 5 is 20. Times 2 is 40. So 9 plus 40, that gives us 49. Now, I can almost guarantee you if this turns out to be like a multiple choice question on the test, one answer will reflect the value of 49, another answer will reflect the value of negative 31, which is what we would get if we subtracted instead of adding the 40. So that's a trap that we want to be careful of, and unfortunately that's the way that we have to ask our multiple choice questions to make them somewhat challenging and making sure everyone's understanding the problem thoroughly. So it's not that we want to trick you, it's that we do have to challenge you to make sure you are calculating things properly and thinking about things properly. And so what does it mean if we have a value of positive 49? We just said that if it's positive, we have two real solutions. And so that would be our answer here. Exactly, yeah. When we have this minus 4, we can consider that a negative 4. And then with a negative here and a negative here, we know it does turn to a positive. Because when we multiply a negative times a negative, it is positive. Okay. One last problem I want us to look at. Let me jot something down real quick. Sorry about that. Okay. So let's say in this example, an object is thrown upwards with an initial velocity of 32 feet per second. From the top of a building that is 48 feet high. How long will it take for the object to hit the ground? Okay. Now, if this were a calculus or a physics class, we wouldn't give you the formula for this, but since this is an algebra class, we need to give you the formula because you haven't yet learned how acceleration and velocity and position are all connected. So let me go ahead and give you the figure. The height after time t is negative 16t squared plus 32t plus 48. Now you can probably see where the 32 and the 48 have gone. That's those two parts of the equation. Does anyone know where this number comes from off the from previous classes? I'm just curious. It's okay if you don't know. Does anyone know why we have this negative 16 in front? Negative 16 is half of 32, although it is a coincidence in this case. Acceleration due to gravity, exactly. Now I've actually rounded it to make the problem a little bit easier for us to calculate. But when we think about when an object is thrown upwards, or even if it's thrown downwards, it doesn't matter which direction we're throwing it, from the top of this building, there's really two things that are acting on it that we have to keep track of. The initial velocity that the object is propelled at, and we have to remember that gravity is affecting these objects as well. So the next negative 16 actually comes from acceleration due to gravity. In feet per second, the gravity on Earth is usually we consider it to be 32.2 feet per second. Although we sometimes round it to 32 just for simplicity's sake. A lot of the time, though, you see it in metric as 9.81 meters per second. But yeah, that's where this number is coming from, and we don't really need to understand that to be able to work this problem successfully, thankfully. Because most people at this point haven't taken a physics class, or it may have been a while since you last had a physics class, which is fine. But yeah, that's where that number is coming from. But if this were like a physics classroom or like a calculus 2 class, for instance, then I would expect my students to know exactly where that number came from and how to plug that in. Depending on whether we're using standard units or metric units, then that would tell us what value to use there. It ends up being negative 1/2 times gravity is the actual formula. So the real formula is negative 1/2 times gravity times t squared plus the initial velocity times t plus the initial height, which is these two numbers, initial velocity, initial height. So we plug those in, and then the gravity actually gives us the other one. Anyway, the point is, you don't have to worry about that. The question is, how long does it take for the object to hit the ground? Well, if this equation models the height, what will the height of the object be if it's on the ground? If the object hits the ground, how far is it off of the ground now? Zero, yeah. If it's on the ground, then its height is 0 feet above the ground. So since we know it hit the ground, we'll plug in 0 for the height. and set that equal to our equation. Okay. It's okay. It's okay. Yeah, sometimes we get to a point where we feel like it's a trick question or something, but in the reality is if something's on the ground, it's just at 0 feet off the ground. Yeah. Sometimes it's just letting our minds be open and not trying to figure out what the trick is. It's just the fact in this case. I would recommend that we factor out a negative 16 in this case. So we have, I picked these numbers in particular because they all have 16 in common. The reason I would want to take out a negative 16 in particular is so that the square term, the t squared term, comes out to be positive. So by taking out that negative, that leaves this as a positive number. And so oh, yeah, that's fine. I'm just trying to wrap up real quick. I'll make sure to post the homework. So if y'all need to take a break and get to your next class, that's fine. I'm going to go through this really quickly, and that'll be it. But this will be in the video, so don't worry about it. So we end up with two solutions when we factor this, which is t equals 3, t equals negative 1. So the question is, does it take 3 seconds, or does it take negative 1 seconds to hit the ground? And it just doesn't make sense to say something takes negative seconds to hit the ground. So our answer is 3 seconds. All right. Pearson account is not required. That's just for the people that if you bought an ebook or you bought an access code from the bookstore for your textbook, then you'll need the course ID that I posted to be able to access that. Yes, absolutely. And that's where the problems are coming from, is the Sullivan book. Okay. So that'll be our homework for today. I'll make sure to post a copy of the textbook pages that have these problems on them. That way, if you still don't have a book yet, or just you want to real quickly look it up on Canvas where the problems are, that's fine. But let me know if you have questions. Just go ahead and practice these. Again, these are not to be turned in. It's really just for practice, but I do hope that you look at each of these before we get to our Monday class. I hope you all have a good rest of the week and enjoy the weekend, and I will talk to you all again on Monday. Y'all take care.